Okay, since we are 17 people here, almost 20, we can start our talk. This is the 10th talk of astrophysical talk series organized by Istanbul University Observatory. And today, in the 10th talk, our speaker is Alex Cooper from Amsterdam University. He's a PhD candidate in theoretical astrophysics group in Amsterdam University. He took his bachelor degree from Nottingham University. His studies include both theoretical and observational aspects in high energy astrophysics phenomena. And today he will give a talk titled Do Magnetars Power Fast Radio Bursts? Okay, Alexander, first we would like to thank you for accepting to give a talk here in this series. So it's your turn now. You can share your screen and you can start. Thank you.
Thank you very much. Can you see my slides already? Oh.
Yes, perfect.
Yes, we can see.
Cool. Yeah, thank you very much for inviting me. It's really nice to be here virtually. So yeah, as you said, I'm a PhD student. I'm a final year PhD student at the University of Amsterdam. And today I'm going to talk about magnetars, fast radio bursts, and trying to answer the question whether magnetars power all of the fast radio bursts that we see. And this is work I've done primarily with my two supervisors, Ralph Wires and Antonio Rowlandson. So what I'd like to do for the first few minutes is kind of bring you on a brief history of all of the observations of fast radio bursts in the last few years, to try and understand why we think they might be powered by these highly magnetized neutron stars. So this all started many years ago now with the Lorimer burst in 2007, and it's named for its discoverer and his collaborators, Duncan Lorimer. And this is data taken by the Parkes telescope, and they were reanalyzing this data for peculiar or far away pulsar-like emission. And what they found was something really interesting. So they found a millisecond radio burst that you can see here. And it was interesting for a couple of reasons. Firstly, it was very, very bright at 30 Jansky. And secondly, it appeared that it was very far away. So we have this sweep across the time and frequency from this radio emission, and this is caused by the dispersion delay. So as the radio waves propagate towards us, they interact with electrons free electrons along the line of sight. And this interaction happens more readily at lower frequencies. So you get this sweep across the band, which is due to the propagation effects. And because this depends on the number of electrons between you and the source, you can correct for this and find something called the dispersion measure, which is a measurement of how many electrons are on the way. And this can tell you something about how far away the source is. And it's not a perfect science, but at least the approximate dispersion delay for this burst meant that it seemed very, very far away, extragalactic in origin. And this, coupled with the very bright burst, suggested that it was extremely powerful, much more powerful than anything we've seen from our own galaxy. So following the first fast radio burst, there was a few years of kind of doubt. So there was one weaker burst discovered by Parkes in 2011, but this wasn't very convincing evidence. And because nothing else had been seen similar to that first burst, there was some suggestion that maybe this was a very high dispersion measure pulsar within our galaxy, or possibly some very strange terrestrial interference from here on Earth. And this kind of doubt wasn't helped by the fact that these strange Peryton bursts were also found at the Parkes telescope. And so the weird thing about this, again in this old archival data, was that all of these things that looked very much like fast radio bursts happened around the same time of day, just after about 12 o'clock in the middle of the day. And of course, you don't expect an astrophysical source to only emit bursts at you, around lunchtime. So this was kind of evidence against possibly the reality of fast radio bursts. But this all changed in 2013 when it was confirmed that 4 more fast radio bursts had been discovered by Parkes, the telescope in Australia again, implying that these things were real and these things that were cosmological in origin. So the first rate of fast radio bursts was confirmed to be approximately 10,000 per day per sky. So if you had a radio telescope that could see the entire sky, you would see about 10,000 of these fast radio bursts. And here you can see the 4 bursts in terms of dispersion measure and location away from the galactic plane compared to all of these other galactic known sources. And these are the light curves for these bursts. So now we've seen a few of these. It was becoming much more interesting to try and follow up this and see it with other telescopes. In addition to this, it was finally understood what was causing these strange lunchtime bursts, and it turns out it was to do with the time of day. So as people were cooking their food in the microwave, if they opened the door slightly too early before the timer ran out, the radio instrument would pick up something that looked very much like a fast radio burst, but wasn't. So now we'd seen more of these things. We'd discounted these strange Peryton bursts, and some other telescopes started to try and find these properly. So the first non-Parkes telescope burst was discovered by Arecibo, pictured here on the right. And of course, this is further confirmation that these things were real and astrophysical in origin. And then another big breakthrough came in 2016 when the first repeating fast radio burst source was seen. And so this was from the now famous source FRB 121102, where we saw many bursts from the same patch of sky. And this implied that at least some of these fast radio bursts were being powered by a mechanism that wasn't cataclysmic. So it wasn't ending the life of the source, something like a neutron star merger, which had been hypothesized, or a supernovae or evaporating black holes. At least some of these sources had to produce many fast radio bursts over their lifetime. The next kind of step in terms of observing these things was to try and localize them to a source, or to a galaxy at least. So many of the fast radio bursts that were seen in these survey instruments where you don't have a good localization on where they're coming from. And people were trying to do this with various radio telescopes. And so the first repeating source that I mentioned before was localized to a high star formation dwarf galaxy at about 1 gigaparsec. So definitely cosmological in origin. And you can see some of these localizations here. And to date, about 20, I think 21 now, fast radio burst sources have been localized to a specific host galaxy. And this is an image of one of these really nice localizations where you can really see that the fast radio burst source itself is sitting in one of these spiral arms of this galaxy. 2020 was a very big, important year for fast radio burst observations. For the first time, we saw at least something that looked a lot like a fast radio burst from a galactic magnetar within our Milky Way, magnetar SGR 1935. So this was a burst seen by 2 separate instruments. The CHIME FRB collaboration in Canada saw 2 separate bursts separated by about 30 milliseconds. And also the STARE-2 collaboration, which is an all-sky radio telescope. So they're only very sensitive to extremely bright bursts like a galactic FRB. And so you can see where this burst lies here. And this is a plot of all of the radio transients we know of, really. On the y-axis is the spectral luminosity, and on the x-axis is the duration of the transient. And so it sits just below where we think, where all of the fast radio bursts lie. So it's a little bit less bright, but that makes sense because it's much closer. We're able to detect it. So it really does seem like magnetars would be a good source model for these fast radio bursts, given how close this is to the FRBs in its characteristics. One of the really nice things was that this magnetar burst happened at the same time as a very active period for SGR 1935. And you can see in this bottom panel, these are X-ray bursts, and you can see how many magnetar X-ray bursts were identified in the time around when we saw this galactic FRB. And this meant that many X-ray telescopes were pointing at it. And so we actually did see, quite remarkably, an X-ray burst simultaneous or nearly simultaneous with this fast radio burst. And the interesting thing here is that it had a very strange spectrum. So if you look in this figure in the top right, you can see the photon index for, in gray, are all of the other X-ray bursts that were discovered around the same time. And right over here, separated from all of the other X-ray bursts, was the one burst that was seen associated with this fast radio burst. And so it really had a strange spectrum, and that was might be key in trying to identify how these fast radio bursts are powered, if there's a relationship between the X-ray emission from magnetars and the radio emission. Again, in 2020, there was interesting results from the CHIME FRB collaboration, who also discovered that fast radio burst, and they published their catalog. With over 500 fast radio bursts. And because there's just so many that they've seen, they're able to do some really interesting statistics already. So on the left here, there's 4 panels of typical bursts that they see separated into these categories. So the 2 panels on the left make up about 90% of the fast radio bursts that they see. And these are characterized by a single peak of emission. In about half of cases, this is broadband across the entire CHIME bandwidth of 400 to 800 megahertz. And in about 60% of all FRBs, this is very narrow band. So we really only see emission in this narrow band of about 100 megahertz in this case, which is something to explain if you're trying to model these fast radio burst emission mechanisms. In about 10% of these cases, we see more complex morphology in time. So about 5% have 2 peaks in the radio data, and about 5% of all bursts have a much more complex, either 3 or 4 or sometimes up to, I think, 7 peaks in the fast radio burst itself. And each of these subbursts is seen at different frequencies. And this is something that we see in a lot of fast radio bursts, is this drift down in frequency as a function of time. Again, interesting to try and explain if you're going to make models of these fast radio bursts. Another thing that CHIME were able to look at was the differences between one-off FRBs and these repeating bursts from the same source. And so here you can see they've plotted many of these one-off and repeating bursts as a function of the bandwidth of the emission and the duration of the fast radio burst. And we can see that one-off events seem to look slightly different to these repeating fast radio bursts. So they seem to be more broadband in nature, and also possibly slightly shorter in duration as compared to the repeating bursts. So this may be suggestive of, for example, a different radiation mechanism or a different source origin of these 2 types of fast radio bursts. The most recent, I think, result that I'll talk about for now is the periodicity that's been discovered in, I think, 2 fast radio burst sources now. So this is in the repeating source. What we've seen is that there's periodic active windows of emission. So this is a plot of many observations that occurred for about 1.5 years. And these gray bands here are the only periods in which fast radio bursts were seen from this repeating source. And so this occurs every 16 days or so. There's an active window for about 4 or 5 days. And that's the only time we see these fast radio bursts. And this is a big clue because it challenges some of the notions that we have about magnetars, at least the magnetars that we've seen in our galaxy. So I'll talk about that in a little bit. So why do we think that magnetars are a likely culprit for powering these fast radio bursts? Well, the first thing we can do is just look at what we've seen already. And in terms of coherent emissions, this is emission that's brighter than the sum of the radiating particles. We see that most of the coherent emission we've observed comes from neutron stars. So this is a plot, again, of all of these radio transients from, on the y-axis, we have the spectral luminosity, and the x-axis, again, is the duration of the transient. And all of the emission in this kind of white region here is usually powered by neutron stars. So pulsar emission, giant pulses, and then fast radio bursts lying up here at much higher luminosities. And one way to explain this is that this very high luminosities might imply a very strong magnetic field, as you would have, for example, from a magnetar. Another really interesting link between magnetars and fast radio bursts is if you look at the statistics of many bursts. So in this table, we have two magnetars, SGR 1900 and SGR 1806. And we also have the first repeating source, FRB 121102. And so what we have here is some statistics based on for the first line, how long is what's the distribution of time you have to wait if you've just seen a burst to see another one? And so for the magnetar X-ray burst, if you've just seen an X-ray burst from this magnetar, this distribution of waiting times is well fit by a log normal with a mean of around 50 to 100 seconds. And we see a very similar thing for fast radio burst from this repeating source 121102. And then in the second line here, we have the luminosity function. So how many bursts do you see at different energies? And again, they're both well fit by the same kind of distribution. So a power law of around 1.6 to 1.8. And so it's possible that there's a link between the emission mechanism or the energetic mechanism powering these X-ray magnetar bursts that we see in our galaxy and these fast radio bursts that we see from extragalactic sources. I'll just mention a few other important factors. So we see close to 100% linear polarization within one of these fast radio bursts. And normally this is indicative of very strong organized magnetic field lines, which you'd expect to see from magnetars and neutron stars. Within one fast radio burst, we see a polarization angle swing across the polarization angle as a function of time. And we also see this downward drifting time frequency across individual bursts. So you can see this on this figure on the right. As the burst continues, you see emission at lower and lower frequencies. And these are two things that can be explained relatively well in a pulsar or a magnetar-like emission model. And these are things that have been seen in pulsars as well. Of course, we have seen the mini FRB from the galactic magnetar, as I mentioned, which is very strong evidence that at least some fast radio bursts come from magnetars. But it's not all clear, so there's some puzzles. So specifically, this long-term periodic active windows is slightly difficult to explain in a magnetar setting. The reason for this is that all of the magnetars that we know about in the galaxy, or at least the vast majority of them, have spin periods of 3 to 10 to 12 seconds. And so this long-term periodicity isn't easy to explain in terms of the spin period of the magnetar. And also, we haven't seen any magnetars in our galaxy in a binary system, which is another way you could get this kind of periodic emission. But this is still a leading theory of how these magnetars can produce this long-term periodicity if they have very long spin periods. Also, some of the localizations are not necessarily where we'd expect. Sorry, I'm just going to stop my cat from. Sorry, I don't know if you heard that, but my cat was playing with a plastic bag. So anyway, yeah, so some of the localizations of these fast radio burst sources are not necessarily where we expect magnetars. So regions very far away from star formation regions, we don't expect young magnetars to be there. And so that can be challenging for this kind of magnetar picture of fast radio burst emission. So that's kind of the observational side. And now I'll briefly discuss some of the competing models that we have of magnetar emission of fast radio bursts. So at the start, in the kind of early days of radio burst emission, there was, of course, many theoretical models that people were coming up with to explain this fast radio burst phenomena. ranging from merger events, as I mentioned, to black holes, to alien light sails. But thankfully, most of the people working on it now have kind of converged onto two classes of models of fast radio bursts from magnetars. And so these can be broadly split up into the far-off models, sometimes called the GRB models, where emission occurs very far away from some central engine that's often a magnetar. And the close-in magnetospheric models, where this coherent emission is occurring very close to the neutron star surface. And some examples of the former is the synchrotron shock model, and an example of the latter is coherent curvature radiation, which I'll talk about in more detail. So in terms of the specific models, in the synchrotron maser shock model, you have relativistic magnetized shocks that are moving away from some central object or central engine, often presumed to be a magnetar, but it could be, for example, an X-ray binary or other progenitors, as long as you have this relativistic blast wave. And in front of these shocks, you have conditions that allow astrophysical masers to produce coherent radiation. And this is one theory of how you can get these fast radio bursts. And so it's been shown that these can explain the time frequency properties, this downward drifting time frequency structure within the context of this model. And I think most importantly, this kind of fast radio burst emission has been reproduced in these particle in cell simulations. And this is really kind of strong evidence that this could be a theory that is viable to explain fast radio bursts, because it's very difficult to do these kinds of simulations for other models. I think some of the more difficult things to explain within the context of this model are the specific properties of fast radio bursts. So, for example, the polarization angle swing across one burst is relatively difficult, and also things like nanosecond variability and two bursts separated by a very short amount of time. Because you're looking at much longer length scales and the emissions occurring further away from the neutron star, it's relatively hard to reproduce this kind of variability. In terms of the coherent curvature radiation model, so that's an example of one of these magnetospheric models of fast radio burst. These require bunches of charges, and the proximity of these charges together, if you have many electrons very close together, you can produce coherent radio emission through curvature radiation. And so we know that this must occur very close to the neutron star surface. You need very large magnetic fields of about 10 to the 14 Gauss to be able to produce these kinds of bursts. And people have looked at this model in terms of the galactic FRB, the magnetar burst rates, also making predictions of coincident X-ray emission, and they seem to be consistent with what we've seen, our observations of both fast radio bursts and of magnetar bursts in the X-ray band. Again, this model can reproduce this downward drifting time frequency structure that we see in these fast radio bursts, and some of the specific spectral properties that we see. So it seems to fit the data relatively well, and it's quite a flexible model in that respect. I think the difficulty here is trying to understand how exactly you form these bunches of particles before the emission it's possible to have coherent emission. So I'll talk a little bit about this bunch formation and in more detail about the magnetospheric emission and this curvature radiation model. So one way in which you could have these bunches, well, first you need to accelerate these particles to high energies, and you need an electric field to do so. And one way in which this is possible is if there's a crustal event on the surface of the neutron star which dissipates magnetic energy. So for example, some kind of star quake or motion on the crust of the neutron star can dissipate magnetic energy, and this flows out from the neutron star in the form of Alfven waves. And so as this Alfven waves move away from the surface, they move into regions of lower charge density. And as the density drops below some critical value, because you require a current to support this Alfven wave essentially, and you can get this very strong electric field that develops, and this leads to particle acceleration. of these charged particles. In terms of the bunches themselves, as these particles are accelerated, particles and antiparticles are accelerated in different directions, and this can lead to bunching due to something called the two-stream instability. And it's thought that these bunches occur on these typical length scales of about 1 centimeter, and that can provide the conditions for coherent curvature radiation. So what is coherent curvature radiation? Essentially, as particles are accelerated along magnetic field lines, because the magnetic field in the region is very strong, all of their motion perpendicular to the magnetic field is radiated away very quickly. And so they're kind of stuck to these magnetic field lines as they flow away from the neutron star. And it's the slow curvature of these field lines, because of the dipole nature of the neutron star, that leads to an acceleration, because the particles are changing direction, and that leads to radiation. And for each one of these coherent bunches, if we assume the properties for coherence are met for one bunch of n particles, then this emission goes as the number of particles squared. And that's what can really power these very bright, fast radio burst emission. And so the two kind of necessary requirements for a bunch of particles to be radiating coherently: firstly, you need the particles to be well aligned, so they should be pointing in the same direction up to a factor of 1 over the Lorentz factor gamma here. And also you require that the particles are relatively close together. So at least the radius of the coherently emitting region is smaller than the Lorentz factor of the particles times your observing wavelength. And these two conditions will be quite important for what we'll discuss in a bit. So what we're going to do here is take the position behind one of these bunches of charged particles. So imagine this green blue blob is a bunch of particles, and it's moving into the screen away from us along these curved magnetic field lines. And so the magnetic field, the very strong magnetic field from the neutron star, goes into the page here. And what we find is, because these particles are traveling at nearly the speed of light, there's a very strong current associated with their motion, because you have a bunch of charges moving, which leads to a current. And of course, whenever you have a current, you have a magnetic field. And so we have this magnetic field component due to the motion of these charges that's perpendicular to this very strong neutron star magnetic field line. And what does this mean? Well, it means the sum of the magnetic field of both of these components, this induced component and this neutron star component, is actually a twisted magnetic field. And so it looks something like this corkscrew, right? You have this long, slow curvature from the neutron star, and the electromagnetic effect of this bunch of particles twists up these magnetic field lines. And so each of these particles follow this twisted magnetic field. And what we do in this paper is try and understand what the effect of these twists are. So the first effect that we have is that we think there's a maximum luminosity because of this twisted magnetic field that any of these particles can have. So if you remember, one of the conditions for coherence is that the particles should be well aligned to within 1 over gamma. And so this alpha, which is essentially how twisted up these magnetic field lines are, is proportional to this induced magnetic field, this perpendicular component, and the neutron star magnetic field. And this should be less than 1 over alpha. Another way of saying this is with this expression. And by substituting in this perpendicular component, we can find that there's a maximum Lorentz factor that these particles can have, such that the emission can still be coherent. So if you accelerate your particles to higher Lorentz factors than this, there's no longer coherence, and you don't see this bright radio burst anymore. The total luminosity of this coherent emission from this one bunch of particles it depends very sensitively on the Lorentz factor of the particles. And so by plugging in our maximum Lorentz factor we found, we're able to say that there's a maximum coherent luminosity for any one of these bunches that's powering these fast radio bursts. And this depends very sensitively on things like the surface magnetic field, the period of the pulsar, and most importantly here, I think, is that it drops very quickly as you move away from the neutron star, because you're moving into regions of lower magnetic field. And yeah, the maximum luminosity is much smaller as you move away from the neutron star surface. So we think that strong, bright, coherent bursts must occur very close to the stars, the surfaces of these neutron stars. So in this plot, I just show on the y-axis is the spectral luminosity again, and on the x-axis is the surface magnetic field of various neutron stars. So the magnetars would kind of live up here, and in the background we have typical coherently emitting luminosities, so giant pulses, pulsars, the galactic magnetar, and the Crab nanoshots. And these lines represent the maximum luminosity attainable by a bunch of particles from a neutron star with this strength. And again, this is right on the surface of the star. So if you move one neutron star radii away, this drops quite significantly. And what we see is that in general, the brightest fast radio bursts require a very strong surface magnetic field of the neutron star to be able to emit at the kinds of luminosities that we observe. So the second implication of this twisting of the magnetic field lines in the context of this model is that we expect high energy emission. So individual particles still have to follow these curved magnetic field lines, but they're now also following these small twists as well. And in terms of the actual individual particle acceleration, this is very similar to a synchrotron-like emission, right? Because you're gyrating around a central point, but the pitch angle is very small, and it's proportional to this induced field over the neutron star field. So we think that there's simultaneous emission in two bands because of this acceleration on these two very different length scales. So the large scale motion of the bunch of particles along these curved magnetic field lines leads to coherent radio emission, as we've been discussing. But on an individual level, each of these particles undergoes very small gyrations. And these, of course, lead to an acceleration, which leads to radiation in higher frequencies. And most of the time, this seems to come out as X-rays. And this is incoherent X-ray emission. And so this kind of simultaneous X-ray counterpart to these possible fast radio bursts could explain, for example, high energy observations of neutron stars in our galaxy, and possibly even contribute towards this X-ray burst that we saw with this galactic magnetar. So I mentioned that it had a very strange spectrum. This peculiar spectrum could come from this component here, this high energy component. And the important point here is that because this X-ray component comes from the same set of radiating particles, the same bunch of particles, you would only see that emission if the radio emission was also pointed at you. And this would explain why, for example, we saw hundreds of X-ray bursts with a different spectrum to the one X-ray burst we saw coincident with the fast radio burst from SGR 1935. So for the last couple of minutes, I'll very briefly mention something else that I'm working on, which is related in a similar vein. It's radio precursors to neutron star mergers. And this was something that was discussed in the early days of fast radio bursts. Could neutron star mergers power at least some of these fast radio bursts? So we now know that the rate of neutron star mergers is 1 to 2 orders of magnitude too low to explain fast radio bursts. And of course, we've seen repeating sources now, which makes it less likely that they come from neutron star mergers. However, it's still really interesting to be able to probe this kind of emission, particularly, for example, if it occurs before a merger event, and you can get these multi-messenger detections of the same source. So what we do in this paper is we look at whether normal pulsar-like models could explain or could lead to cosmologically observable radiation before the merger itself. So in this figure on the right, you can see that this is by Lujakov et al. 2019. This is, you assume that one of these neutron stars is highly magnetized, 10 to the 12 Gauss or so, and one of them is much less magnetized and acts as a conductor. So as it moves through the magnetic field of the primary neutron star as they in spiral, this conductor expels the magnetic field. So the blue lines here are the magnetic field lines of the other neutron star. And the expulsion of this field around the surface of the conducting neutron star leads to a very strong electromagnetic response from the conductor. And it leads to these patches that you can see in these corners here, a very strong electric field parallel to the magnetic field. And that is an important point because it means that particles that are in the vicinity will be accelerated along these magnetic field lines in a very similar vein to coherent curvature radiation, or in a normal pulsar, you see the same kind of thing. And what we find is that these this emission could be observable if you have a large enough surface magnetic field from your primary neutron star. So if one of your neutron stars is magnetized, you can see this. And the kind of fluxes that we see increases the time to merger decreases. And this could possibly be observable out to hundreds of megaparsecs with some assumptions about how the pulsar emission comes about. And what we're able to do here, which is probably one of the most interesting parts, is we're really able to map the electric field as it develops around the conducting neutron star. So this is a map of how the electric field develops in the orbital plane. And using this, we can really pinpoint exactly where the emission is going to be directed. We know where the magnetic field lines are. We know where these regions of very strong electric field are. And so we can make these viewing angle dependent light curves. And here is an example. And so what we find is so that differences in phases run down the page, and differences in the viewing angle, the inclination angle to the orbital plane run across. And so we find that there's small windows of 5 to 10 degrees where you really see most of this emission. And this emission is modulated by the orbital frequency. And so you really see this as small bursts of emission every time the field lines that you happen to be aligned with get very close to the other neutron star. And so we think that this could be detectable through, for example, triggered radio observations of gamma ray bursts, of short gamma ray bursts, or gravitational wave events. And it really depends on the kinds of efficiencies as to whether you would see this or not. But with the SKA, it's definitely testable. So I think I'll stop there. I'll just mention some conclusions. So at least some fast radio bursts are emitted by magnetars. If we have very bright coherent curvature radiation, this should occur very close to a neutron star surface in regions of very high magnetic field. And all bursts powered by this mechanism of coherent curvature radiation should have a non-thermal X-ray counterpart, which may be quite weak. And lastly, coherent bursts from neutron star mergers or precursors to neutron star mergers could be observable to hundreds of megaparsecs. Thank you very much.
Thank you, Alex, for this very nice talk. So I'm sure there will be some questions from the audience. So if there is any question, I see one hands up. Erbil.
Thank you very much. My question is about the Galactic FRB. FRB 2004-28 is about 40 times fainter than the cosmological FRBs, the bottom end of the cosmological FRBs. What can be the reason for that? Due to a selection effect, that is, we are not able to detect faint, less energetic FRBs from cosmological distances, or are there more than one mechanism and also magnetospheric places that can produce FRBs?
Yeah, no, you're absolutely right. It's definitely we wouldn't be able to see that burst from cosmological distances, so that's one consideration. I think because we don't know the nature of the sources that are producing these cosmological FRBs, there could be a difference in the type of source or the type of magnetar in this model that can produce very bright bursts versus slightly less bright bursts. For example, there's some ideas about whether the surface magnetic field of a magnetar or the period of a magnetar has to be, for example, very high in both cases to produce the very, very bright burst that we see. So there could be a difference between the magnetars that we have in our galaxy. But again, we don't really know because of these selection effects, as you mentioned.
Thank you very much.
Thanks.
Is there any other question? Yes, Ersin Göğüş.
Hi, Alex. Thank you very much. Very nice talk.
Thanks.
I have a general curvature radiation question. From geometric point of view, what ensures that curvature radiation occurs always around the same region so that the cone of curvature radiation points at us? In other words, what's the likelihood that we will see that region emitting curvature radiation and magnetic field structure would change? We observe it in the phase of giant flares, for example, and the curvature radiation might shift a little bit so that it's not pointing at us anymore.
Yeah, no, absolutely, you're right. I think it's very likely that there is many more fast radio bursts than the ones that we see. So at least in the curvature radiation picture, these bursts are beamed to a factor of 1 over gamma. So there may be 100 times more bursts going off that we don't see. It's also possible that we are preferentially aligned, let's say, with a particularly active region on the neutron star surface. So I can imagine a situation where you have a precessing magnetar, for example, and the active region on the surface points at you more of the time than not, for example. But yeah, it's definitely an interesting question in terms of the behavior of the magnetar, and could tell you something, for example, about the period or the precession of the magnetar as well.
Okay, thank you, Alex. Is there any other question? So if not, we thank you, Alex, again for giving this talk here, and we also thank for the questions, contributing questions. So see you in our next talk.
Thank you very much.
Thanks, Alex.